black holes. If some of you are here to get extra points for your English grade if you are in second year, but even if you are not, for our statistics, I would like you to click on the link I just sent, which hopefully should lead to a Google document with your name and your first name already, since you already signed up on Moodle. You just need to say yes if you are here today in the first column. Then you just need to add your major, your year of study. If you are biomip or CMI, or biomip, biologie, renforcement, maths et info. So if you don't know what it is, you are not a biomip student. Same thing for CMI, cursus master en engineering. If you don't know what it is, the answer is no. And that's all for me. So I'm now going to give the floor to our guest, Nathalie. Are you ready? Thank you.
Can I share my screen?
Yeah, sure. Hopefully it's going to work.
Let's hope so. Let me just check it's turning slides okay.
We can hear you.
The hospital and you have an x-ray to try and see if you have a broken bone, for instance. And it's a good way to try and find not only black holes, which I know are of interest to many of you, but other strange and weird objects that exist in the universe. So just to introduce myself briefly, I'm an astrophysicist at the Institut de Recherche en Astrophysique et Planétologie here in Toulouse, in France. And I work mostly on observations in many different wavelengths, but also in the X-rays to try and find some very weird and strange objects that could possibly exist in the universe. So what I'm going to talk about during this talk, I'm going to talk about some of the very strange and extreme objects in the universe, and you'll see why I call them extreme in a few moments.
Excuse me?
Yes?
We cannot see what is writing on the PowerPoint.
Sorry?
It's very pixelated.
Is it the same for everybody?
Yeah, I think because in that chart, they are saying this.
Okay.
It depends. At the moment, it's fine.
Okay.
But 2 seconds earlier, it wasn't.
I guess it's probably because it takes some time to maybe load. Is it still very pixelized?
No, at the moment.
Okay. Okay, so then I'm going to talk to you a little bit about X-ray observations, what we can see, how we can see them. And then I'll talk to you about a few strange sources that exist out there. These are the sources I'm going to talk about: ultra-luminous X-ray sources, tidal disruption events, and compact object mergers. And they'll become clear what these objects are in a few moments. And then after a short conclusion, I'm going to show you how you can actually get involved trying to understand what these kind of objects are. So this is the night sky. This is how you can see the sky if you look at the sky with your eyes. If you had a telescope that was powerful enough, you could see all of this. So what are we looking at? This is our way of trying to portray the whole of the universe in a single diagram. It's pretty difficult to portray the whole of the universe in a single diagram, and this is the best we can do. So what we've done is that right in the very center is the center of our galaxy. So you should hopefully be able to see my pointer. And then this band that you can see crossing this oval is the plane of our galaxy. What do I mean by the plane of our galaxy? You probably know our galaxy is a spiral. So you can see an artist's impression of the galaxy, of our galaxy, the Milky Way, in the top right-hand corner. And you can see there's this very bright region in the center. And then we have these spiral arms that spread out. This is an artist's impression because even with the fastest spacecraft that we have, we could not possibly leave our galaxy. It would take many millions of years probably to leave the galaxy and take an image. So we can only see our galaxy from within. And as we're situated on one of these spiral arms around this area sort of thing, and then what we see is we can see towards the center of our galaxy and we can see the rest of our galaxy. So we're actually looking at the galaxy through the galaxy and if it's on its side. So we've cut it through along the side. So what are we seeing? We're seeing some bright area in the middle, and we're seeing lots of black regions. And the reason we see these regions as black is because there's lots of gas and dust in our galaxy that can stop us seeing the stars that are behind the regions of gas and dust. Although it's really annoying that you can't actually see through this gas and dust, it's very important to have this gas and dust because it's from this gas and dust that the stars actually form. So all of this region is our own galaxy. And then the rest that you're seeing is the rest of the universe going out as far as we possibly can see. So this is data that's been taken with the Gaia satellite. Gaia is a European Space Agency observatory that was launched about almost 10 years ago. And what you can see in this diagram, other than the stars, are a couple of bright areas at the bottom. This one here is the Large Magellanic Cloud, and this one here is the Small Magellanic Cloud. There's some of the galaxies that are in our own area of the universe, and they're close enough that we can actually see the individual stars within these galaxies. There are a few other brighter points, and again, these are just clusters of galaxies where you've got large groups of galaxies that come together and that you can see the brightness of the combined light from all of these galaxies. So that's great. We've got the whole of the universe. Well, not quite, because there's only 2 billion stars that are in this diagram. 2 billion's still quite a large number, but we don't go all the way to the edge of the universe. But how can we possibly know which of these stars that you can see in this diagram are interesting? It's very difficult to say, okay, yeah, it's definitely this one here that's interesting that I might want to study some more. So let's have a look at which of the objects I think could be considered as interesting or extreme or mysterious objects, and then we can try and find out how we can find them. So what kind of extreme, strange, weird objects can we find? First of all, we can find supernova explosions. A supernova explosion happens when the star gets to the end of its life. Only the most massive stars explode at the end of their lives in a supernova. A star like our sun, for instance, won't become a supernova, but much more massive ones, maybe 8, 10, 20, 30 times the mass of our sun, will explode at the end of their lives. These events are pretty rare. A star lives for millions and if not billions of years. So we only expect to see a few supernovae every century in our own galaxy. Here's one that was actually discovered thanks to a student project in London. This was during an astronomy lab class. So here what you're seeing is the galaxy M82, which is about 3 or 4 megaparsecs away, so about 12 million light years away. And you can see the galaxy. And when the guys on the 22nd of January pointed their telescope for their lab class in astronomy, they found an extra star, this star here, which is actually not a star, and this is a supernova that they discovered quite by accident. And we'll come back to this object in a few moments when we're going to discuss some of the other objects that we're going to look at. So supernova kind of rare. We don't see so many of them. What's perhaps even rarer, although we do see maybe more of these, and that's because they're extremely bright, are what we call gamma ray bursts. Now, gamma ray bursts were a really big mystery, especially when they were first discovered back in the 1960s. The reason they were discovered was the Americans, during the Cold War, were worried that the Russians were testing nuclear weapons. So they sent some gamma ray detecting observatories into space to try and see whether or not they could detect any gamma ray explosions from nuclear weapon testing by the Russians. And they did actually detect some explosions, and luckily they didn't react straight away. It took them a while to realize that actually the explosions weren't coming from Earth, they were actually coming from space. And they were detecting approximately one of these explosions every day. And this is where they became known as gamma ray bursts, because we detected them in the gamma rays. What these objects were was a real mystery until about 20 years ago or so. And then we discovered that actually they're just, for some of them at least, they're just more extreme supernovae. So these are some of the most massive stars that have ever existed in the universe, exploding and becoming a black hole. They also can be other objects, and we'll come on to that in a few moments. So we talked about the supernova explosions and the gamma ray bursts. What gets left behind after a supernova explosion? Well, usually it's a neutron star. So you can see an artist's impression of a neutron star here in this diagram on the left. Neutron stars are fairly rare. Obviously, they've come from an explosion that's pretty rare. So we find it pretty difficult to detect, not only because they're rare, but also because they're very small. So they're actually about the size of Toulouse only, but they pack in about 1.5 times the mass of the sun. We're not sure exactly of the mass of a neutron star, but it's somewhere between about 1.5 and 2 times the mass of our sun. So the sun weighs about 2 times 10 to the 30 kilograms, just to give you an idea of how massive these objects are. That means that because they're so small and they've got this huge mass, that their density is just ridiculous. So you can see this density here of a typical neutron star, 5 times 10 to the 17 kilograms per meter cubed. And to give you a comparison, the density of water is just 1,000 kilograms per meter cubed. That means if you took a teaspoon of neutron star matter, the matter making up these neutron stars, that would weigh 10 to the 7 tons. So it would be pretty difficult to put in your coffee or your tea in the morning. So neutron stars are very extreme. The matter is very strange on the inside, doesn't behave in the way that the matter you have on Earth. Also, they can have very strong magnetic fields. And in this artist view of a neutron star, we can kind of get this idea of the magnetic fields. They've tried to draw them around here. Because the magnetic field is so strong, it can actually rip the charged particles off the surface and accelerate them around the neutron star in this kind of area. And you can see some of these accelerated particles coming out the top and bottom. And because the neutron star is rotating, it's going round and round, you see these beams of light crossing your line of sight, and it looks a little bit like a lighthouse or like the Eiffel Tower at night with the light beam that's rotating on the top. So we see something like hopefully you're seeing on the right-hand side. So the neutron star has got these two strong beams coming out. And as one of the beams crosses our line of sight, you see much more light than when the beam is not crossing our line of sight. And so we see these pulsations. We see a constant amount of light until the beam crosses our line of sight, and then we see the amount of light increasing and then goes back again. And for this reason, we call these things pulsars. So I'll talk about neutron stars and I'll talk about pulsars, and I might interchange them because they can pretty much be all pulsars. Other extreme objects that can be produced either in the a supernova explosion or in the gamma ray burst are black holes. Now, black holes are even more extreme than a neutron star. We know of different kinds of black holes. These are the three types of black holes that we know of. So we know of stellar mass black holes, supermassive black holes, and these other kind of black holes called intermediate mass black holes. It's kind of difficult to show a drawing of a black hole because by the nature of a black hole, it doesn't actually emit any light. In fact, it absorbs all the light that's around it. And so we can't actually see them, which is why we call them black holes. We can actually see the light that's... Yes?
There are a few questions. Would you like to answer
them now? Okay, I don't want it to come out of my presentation because it's been very difficult to get it to come up and I can't see the chat at the moment. But if you'd like to ask, can you ask the questions and I'll happily answer them.
Okay. Pulsar?
So the pulsar is a neutron star. So you can see this neutron star where you see the emission coming from the poles of the neutron star. And as it crosses our line of sight, you see this pulsation of light every time that the beam crosses our line of sight. So the pulsar is just a neutron star where we see the amount of light changing with time.
And the other question is, how do we weigh stars?
Sorry?
How do we weigh
a star? It's a very, very good question. Excellent. Okay, so the easiest way to weigh a star is when we have two stars together in what we call a binary system. And so the two stars are going around each other like this. In the same way as, for instance, the Earth and the Moon are orbiting each other, or the way that the Earth is orbiting the Sun. So when we have these two objects, there was a very bright guy called Johannes Kepler about 300 years ago that set out three equations that relate the mass of the objects, the speed that they move, and the distance between the two objects. So if you can actually measure the time it takes for your two objects to go around, and you can also measure the distance between the two stars, then you can determine the masses of the two stars that are there. So it's something we do quite regularly, is measure the mass of a star. Are there any more questions?
No.
Okay, I'll carry on. And then if there's anything else, please feel free to interrupt. So yeah, as I said, a black hole doesn't emit any light. In fact, it absorbs all the light in a radius fairly close to it. So the way we often depict a black hole is in the way that it's been done in this image on the right-hand side. So what we're seeing here in this nice colourful area around is what we call space-time. So Einstein told us that we can't describe the universe just in 3 dimensions as you're used to seeing the universe. Usually we see it in 3 dimensions. We need a 4th dimension, and that 4th dimension is time. And you need to take into account all 3 dimensions and the time dimension to be able to understand the universe. And then, if we place a mass in space-time, it will deform the space-time. So if we have a small mass, it will just deform space-time a small amount. But if we have a very big mass, like the black hole, then it will deform space-time a huge amount. And that's going to be important in a few moments because I'm going to talk about the deformation of space-time towards the end of this talk. So the 3 types of black hole we know are the stellar mass black holes, and we know how these are formed. These are formed, as I've already said, through either a supernova explosion or through a gamma ray burst. So that's quite easy. We know that that's how they form. Their masses are somewhere between about 3 times the mass of the sun. So this is the sign for the mass of the sun. And today we know they can exist up to about 100 times the mass of the sun. We also know these supermassive black holes that exist in the center of galaxies. So, for instance, in our own galaxy, the Milky Way, we also see these supermassive black holes. We have one, it weighs about 4 million times the mass of our sun. And in other galaxies, we see them all the way up to about 10 billion times the mass of our sun. So these are huge. But the weird thing about these galaxies is we don't know how they form. It's easy to understand how the stellar mass ones formed. We couldn't possibly have a star that was 10 billion times the mass of our sun that explodes as a supernova or a hypernova or a gamma ray burst to form a supermassive black hole. You could imagine a black hole that forms right at the very beginning of the universe, maybe with 100 solar masses, and as matter falls on it, it's going to get more and more massive. But then we would still not reach these huge big masses that we see 10 billion times the mass of our sun for a black hole that we see today. So it's been proposed that maybe other black holes could exist, these intermediate mass black holes that have masses between 100 and 100,000 times the mass of our sun. And these have been very, very elusive until about 10 or 12 years ago. We found the first good candidate for an intermediate mass black hole here in Toulouse. And that was a good start, but we needed more to be able to confirm that these intermediate mass black holes really do exist. And so I'm going to talk a little bit more about those a bit later on in this talk as well. So what other strange objects that exist? So we can have what we call X-ray binaries, and you can see those in the left-hand side. Again, this is an artist's view of an X-ray binary. You can't, unfortunately, take such a beautiful picture of an X-ray binary today, not with the telescope that exists. An X-ray binary is very simply either a neutron star or a black hole in a binary system, so together with another star. So a star like our sun, for instance. So this is very similar to, for instance, the Earth, moon, or the Earth sun kind of system, where there's the two stars and they turn around each other. And because they're so close, and because the neutron star or the black hole is so dense, it can just suck the material off this star next to it, and so the matter will spin around the neutron star or around the black hole and eventually fall onto that object. It's called a compact object, a neutron star or a black hole. So we see these X-ray binaries, and as their name indicates, they're extremely bright in the X-ray domain, and I'll come on to the X-rays in a few minutes. Another way to try and find a black hole is through tidal disruption events. So if you can imagine a massive black hole in the middle of a galaxy somewhere, we might not be able to detect it because there's no matter around it. But if a star becomes too close to the black hole is going to squeeze and squash the star until it totally explodes. And all the matter can just swirl around the black hole and then fall into it. That's great because a black hole that you might not have been able to see before suddenly becomes bright because of the matter spinning around. And it's one way we use to try and find either supermassive or maybe the intermediate mass black holes. So two other more mysterious objects in the night sky. The first one's a gravitational wave events. So a gravitational wave event, the very first one was detected back in 2015, and today we know about 100 of these events. And they're quite simply when we have a binary system, so again, two stars going around each other, a binary of either two neutron stars, a binary of two black holes, or maybe a binary of a neutron star and a black hole. And what happens is, as we saw in the diagram previously, a huge mass like a black hole or even a neutron star is going to deform the space-time quite considerably. And as the two stars move around each other, they emit these tiny little waves. They look huge in this artist's view of a gravitational wave event, but actually they're extremely, extremely small. And scientists have been trying for 70 years before 2015 to try and detect these gravitational waves come from these strange objects.
There are two other questions.
Yes, absolutely. Okay.
I hope my microphone is a bit better than before. Or let me know if you cannot hear the questions. Why does it serve the star's matter instead of just attracting the entire star, like a ball would fall in a hole?
Is this concerning these gravitational wave events or concerning the X-ray binaries that were on the previous slide?
Maybe David, you could tell us more about your question? David, do you have a microphone?
Oh, yes. My question is why doesn't the star just is attracted by the black hole, and the black hole just sucks the matter?
Right. Okay. So the reason why it doesn't just fall straight in is because the two objects are turning around each other. So pretty much most things are rotating in the universe. It's because there's very little friction. It's a vacuum for most part. So the two objects are going around, and this is what stops the two things just falling into each other. And that's also why the material that comes off the star, for instance, is going to spin around until it loses that energy, angular momentum, and drops into the black hole. So you can't think of a black hole that just like sucks everything up. That's not the case. If, for instance, our own sun became a black hole, it's not possible, but if it did, it wouldn't suck the Earth into it. Earth would stay on its orbit, continuing to go around the black hole. Nothing would change at all. So yeah, we often think of black holes as some kind of huge big hoovers, but they're not quite so. They're not quite such powerful objects in the universe.
Thank you. Could you either switch your microphone off, or maybe I can do it? Well, would that be better? Okay, or I can do it. Okay, I know what to do now. All right, so here is the other question. Okay, let me find it. So about the second explanation related to, is the second explanation related to gravitational waves? Do you mean waves or wells? Wave events, no, probably waves.
Which second explanation?
Jeanne?
Yes?
What was your question?
I haven't got a question. That wasn't my question.
It wasn't your question. Whose question was it then? Who asked the second question? Already answered. There was another question about, is the second explanation related to, oh, Jeanne, sorry, not Jeanne, Jeanne. Jeanne said, you already answered. So, okay.
Okay. If there's any other questions as well, we can always answer them at the end. If it's necessary.
Okay, just remember to switch. Sorry, you might want to switch your microphone off when you are not speaking, because otherwise we'll get an echo when anyone else is speaking. Which is why I decided to mute you. But
okay, yeah, I'll switch it off then when I'm not speaking. No problem. Okay, so these gravitational wave events, we've detected a number of them. There's a lot of things we can find out through the gravitational waves, but we can't, unfortunately, find out everything. And I'll come on to that in a little while. And then very recently, we've had these very strange events that have been going on. We've called them fast radio bursts, quite simply because they are bursts of radio emission that are very, very rapid. They last about 1 millisecond, and it's not clear what they are. They're coming from different galaxies, we know that, but what could be creating such a huge, big explosion is not clear to us. And I'll come back onto those towards the end of the talk. So how can we find these really strange objects, that are very extreme objects? So what we did, we looked with Gaia. I showed you an image where we were looking in visible light. This is the visible light here. You can see what you're used to seeing, the way red all the way through to the blue. So this is what our eyes can see. But there's a lot of other light that we can use to try and detect things. There's, for instance, the radio light. I talked about these fast radio bursts, which are detected in the radio domain. Usually you're familiar with the radio because of the Wi-Fi, for instance. We have microwaves. Obviously, use that for heating your food up in the microwave. We have infrared light. This is usually detected, for instance, from a warm body. So you see this in like spy films where trying to detect people during the night. We have ultraviolet light. You can use it for tanning in the summer, for instance. The X-ray light, which, as I said, you use it to take an X-ray at the hospital usually. That's probably when you're most familiar with the X-ray light. And then there's gamma ray light, which we heard earlier on. It's also emitted from a thermonuclear explosion. So something like a nuclear bomb would emit gamma ray light. So all of the objects that I've been talking about emit strongly in the X-ray. This is because they're very energetic objects. So you can see this arrow at the bottom. If we go towards the left, the radio, then we have the very low energy light. And once we get to the right, in the X-rays and gamma rays, then we get this much higher energy light. So all of these objects I've discussed are all very high energy objects. So how are we going to find them? We're very lucky today to have many different X-ray observatories. This one is the Chandra X-ray Observatory. It was launched in July 1999 and has been observing the sky ever since. This is XMM Newton. This was launched the same year, but in December. Then there's this observatory. It's called SWIFT. It's a NASA mission combined with effort from Italy and from Britain. And this was launched in 2004. This is the New Star mission. I'm going to talk about that in a few moments. And this was launched by the NASA. It's a small NASA mission. These two are very large missions from NASA and the European Space Agency. This is a small mission and is all of this. So the two satellites are actually linked by this long kind of ladder, which was deployed as the satellite was deployed in order to have a long focal length to be able to focus the X-rays between the telescopes and the focal plane. And then more recently, in July 2019, there's this Spectre RG, which was launched. It's a German-Russian satellite. And in particular, it's got this instrument aboard here, which is called eROSITA. And it observes the sky also in X-rays. So what has eROSITA been able to do for us? This is a picture that's been taken of the whole universe by eROSITA. So this is the same kind of thing as we saw with Gaia earlier on. Here is the center of our galaxy, and this is the plane of our galaxy, and this is the rest of the universe. So you can see much further into our own galaxy. We've got much less of this gas and dust that's causing us a problem to see through. And you can see all the way into the very center here. But we see lots of other strange things, and we see some very, very bright things on this X-ray sky. So if we look at this labeled diagram, we can see what we're seeing. So what we found, obviously here in the center, some of this emissions coming from the matter around our own supermassive black hole, which is called Sagittarius A star. If we move around, we can see some supernova remnants. So here is a supernova remnant. This is also a supernova remnant. This is also a supernova remnant. And this one here. And there's also a pulsar, one of these neutron stars that's associated with this supernova remnant here. We can see some X-ray binaries. So this one here, for instance, is an X-ray binary, as is this one up here. We can see some clusters of galaxies. So this is a cluster of galaxies where you get lots and lots of galaxies together, and the gas at the center gets very, very hot and emits in X-rays. We also see another one of those just here. This is also another X-ray binary. It's actually one of the brighter X-ray objects in the sky, along with Vela and with the Crab. So you can see the X-rays is a great way to try and pick out some of these supernovae, for instance, or these X-ray binaries. They're so much brighter and it's so much easier to see them, and we know which ones straight away of these objects are interesting. So X-raying the sky is the best way to pull out these very strange and extreme objects. So what kind of objects do we have? One of the mysterious objects were discovered back in the late 1980s, and they're just classified as X-ray sources with a very high luminosity. That means we're seeing them very brightly in the X-rays. For a source to be classified as what we call an ultraluminous X-ray source, the luminosity has to be of 10 to the 39 ergs per second, and we're going to talk about that number. It doesn't matter about the units, but we'll talk about that number in a few moments. So some galaxies have got these strange X-ray sources that are very, very bright. We know that they're not the central black hole in the galaxy. They're objects that lie outside of the central region. So what you can see in this diagram is an image taken from the Hubble Space Telescope, and that's what's this colored image. And then you can see these contours, and these indicate the positions of these ultraluminous X-ray sources within this galaxy, which is called the Cartwheel Galaxy. And you can see there's about 20 of these ultraluminous X-ray sources. And you can see as well that there's no counterpart in the optical. We don't see them very well in the optical, but we see them very, very brightly in the X-ray. So what they were was not very clear. For them to be so bright, we'd expect them to be something like a big, massive black hole. Why would it have to be a black hole, a massive black hole? Because the luminosity increases as we get a much more massive object. Also looking at the way that the light came from these objects, they seem to be something like a black hole, but it's not so clear. And how do they get so bright? If they were going to be this bright, they should be these intermediate mass black holes that I spoke about earlier. But you couldn't possibly have this many intermediate mass black holes all so bright. That would mean they'd have to accrete a lot of material. Lots of material would need to fall on them to be so brightly, so to shine so brightly in X-rays. What we think they are some object like this. So we have some kind of what we thought a black hole in the center accreting from another star in the same way as an X-ray binary. But matter falls extremely quickly onto the object in the center, the compact object in the center of this X-ray binary. The thing is, there's a problem. In astronomy, there's a certain amount of limits. You might think there are no limits within the universe, but unfortunately there are limits. And there's a limit called the Eddington limit that was defined by Arthur Eddington when he was studying stars. And now the Eddington limit happens because the matter is falling onto the black hole. And so this disk is becoming extremely bright. As it gets brighter and brighter, we see a pressure coming from the radiation, from the light that's coming from that disk, that gets more and more important. You don't usually feel the pressure from the light because the amount of light that's falling on your skin, for instance, from the sun is not very much. But once you've got this huge amount of material that's going around in the disk, it can emit a huge amount of light. And at some point, the radiation pressure, the light pressure, becomes so important that it actually stops any more material falling onto it. So it can't get any brighter. So how do these things get so bright, the ultraluminous X-ray sources? Are they massive black holes? Because we know that the Eddington limit, this limit that we were talking about, scales with mass. So if you have a higher mass, you could see a higher luminosity. Or do we manage to break the Eddington limit somehow? Is there some way to get past the Eddington limit? And if so, how do we do that? Today, we don't know of a physical explanation that could actually tell you how you can get past that Eddington limit. So we tried to study these objects, and one of the ways we tried to make a breakthrough was with this new star observatory that was launched by the NASA back in 2012. So what we're looking at here, it might look a little bit complicated, but it's just like the electromagnetic spectrum that we looked at earlier, but just in the X-ray domain. So here we've got the low energy X-rays, and here we've got the high energy X-rays. You can imagine the X-rays have gone through a prism, and we're just looking at the lowest energy X-rays all the way up to the highest energy. And here we have the amount of X-rays that we're receiving. And what you can see with these black dots and the little lines on them, which are the error bars, are the data that we've taken with missions like XMM and Chandra. And as you can see these black dots going all the way up to about 10, okay, which is 10 kiloelectron volts. For those people who know what they are, the units are not important. We can only go up this far with XMM or with Chandra or even with Swift, for instance. As people say, yes.
Another question. Aren't gravity waves faster than light?
No, nothing can go faster than light. That's the thing that goes the fastest. So no, the gravitational waves are not faster than light. They seem to go approximate the speed of light. That's been tested with the most recent observations that we've taken with the gravitational wave detectors. But no, they're not faster than light.
Thank you.
Okay, so we've observed all of these ultraluminous X-ray sources up to this point with our XMM and Chandra and Swift. And so people have said, how can we understand what is the nature of these ultraluminous X-ray sources? And they said, well, we need to go above there because we plotted what was plotted here and what we did within astronomy was have some models to try and understand the nature of this emission. And there were three kind of competing models. And you can see what these models would do if you go above 10 kiloelectron volts. One of them would go up like this, one would come down like that, and another one would go along here. And the only way to try and understand what was the emission that we're seeing was to try and get data above this point, which is one of the reasons why New Star was launched. So we observed these ultraluminous sources and as soon as New Star was launched, and I'm now going to plot onto this plot the data that came from New Star, and you can see that it follows perfectly this red line here. And this is the line that indicates that, yes, we are seeing emission that's going above the Eddington limit. So now we know that there is emission that goes above the Eddington limit, but we need to find out how. How can we go above the Eddington limit? What is the physics behind it? Why did Eddington say there was a limit, but it seems to be that certain objects can just break this limit for some reason? So this is still an open question, but we know we can go above the Eddington limit now. So whilst we were doing our observations with the New Star Observatory, the supernova that I showed you right at the very beginning went off. Remember the supernova that was discovered during the lab class in London back in 2014. So this is where the supernova is. This is a more colourful image of the galaxy M82. This is where the supernova is. But in this galaxy, there are also some of these ultraluminous X-ray sources, and you don't see them in this image. One of the main goals of New Star was to observe a nearby supernova. And so for that reason, New Star pointed at this supernova for 7 long observations between the 23rd of January and the 6th of March 2014. It was 2 million seconds of observations. So if you could imagine you went to a telescope and you observed at night, you would do that for 2 months every single night. So it's a very long observation, and we had some brilliant data that came from some of the ULXs within that galaxy. So the ULXs are the ultraluminous X-ray sources. And one of those was M82X2, and it has a luminosity which is about 2 × 10⁻40 ergs per second. So we're a factor 10 above that luminosity I showed you, which indicates that this is an ultraluminous X-ray source. Now that we studied this emission that was coming from New Star, and we did a lot of work on it to try and understand what was going on. And the strangest thing happened after thinking that all of these ultraluminous X-ray sources were in fact accreting black holes. We discovered that, in fact, it was one of these pulsars. So this might not seem extremely shocking to you, but a pulsar only weighs 1.4, 1.5, maybe 2 times the mass of our sun. And before we were looking at things like black holes that maybe weighed 20, 100, a few hundred times the mass of our sun. This means that if we have the maximum luminosity, which we said scaled with the Eddington limit, this means we're now 100 times the Eddington limit because it's a neutron star and it's not a black hole. So we've showed already that we can go above the Eddington limit, and that was already quite shocking for us. And now we've found out that actually we'll go 100 times the Eddington limit. So you might think, oh yeah, well, this is just an exceptional object. Maybe there's just one of them. But since 2014, we've now found another 7 of them. No, we found 7 in total, another 6. So lots of questions we're asking ourselves, how can they really get to be so bright? 100 times the Eddington limit. And also, do all ULXs, all these ultraluminous X-ray sources, really have neutron stars as their accretors? So this is kind of a big question that we're trying to understand at the moment. The other amazing thing is that so much material is being thrown onto this neutron star in this kind of binary system. And every time a bit of material hits the neutron star surface, it's still got a little bit of rotation. And because there's so much material that's been thrown onto our neutron star, every time it gives it a little extra knock and a bit more of a knock and a bit more of a knock, so that the neutron star is actually getting faster and faster and faster. And so in this diagram right at the very bottom, you can see the date. Here we're in 2016 and we go up to 2018. And here you can see the pulse period, the time it takes for us to see this bright pulse coming round again. So back in 2016, it took 45 seconds for the neutron star to spin on its own axis. And now in 2018, it's only taking 18 seconds now to spin on its axis. So we've managed to spin up something that weighs nearly twice the mass of our sun to go from 45 seconds in rotation all the way to about 18 seconds in rotation. It's something we didn't think was possible, and that it helps us to understand how we can explain what we call millisecond pulsars that rotate much, much faster than what we're seeing in this image. They can rotate up to 1,000 times per second. And so they're probably formed in systems like this, which accelerate faster and faster and faster, the neutron star, until they arrive at periods of milliseconds. So that's one kind of strange object. I mentioned the tidal disruption events right at the beginning. So tidal disruption events like this that you're seeing in the image, they help us to find these black holes that are normally not bright because the star gets squashed until it disrupts completely and the material spins around the black hole until it falls inside, so it becomes brighter. Now, we can only see these for black holes that are less than 10 to the 8 solar masses, so less than 100 million times the mass of our sun. The reason being is that otherwise the disruption occurs inside the event horizon where we can't see any more light. So although this will happen for big, massive black holes, we can't actually see them because all of that happens within the event horizon. So that helps us pick out the less massive, supermassive black holes or the intermediate mass black holes. And it allows us to try and find them as they become very, very bright when it happens. But these tidal disruption events are quite rare. There's only one tidal disruption event per galaxy per 10,000 years. So they're not very frequent, but we do know a lot of galaxies, so it does allow us to find some. And indeed we have. This work has been done mostly with the Expo Newton Observatory, but also using the Chandra Observatory and the Swift Observatory to help out. So where it says an X in these diagrams, that's XMM, the C is Chandra, and the S is Swift. So what are we seeing in this diagram? Well, in this picture that we're seeing on the bottom right, we can see lots of galaxies. There's a big, massive galaxy in the center and many, many other galaxies all around. You can see them. So this is a cluster of galaxies. And the object that we found was a very faint galaxy. And what you're seeing, why it's so bright here, is because we put the X-ray emission on there, on this optical image. And it was very, very faint in X-rays. In fact, so faint that it wasn't detectable. And all of a sudden, it got extremely, extremely bright. And that's what we're seeing in this diagram here on the left. So this is the time. This is time 0, where there was no light coming from this in the X-rays from this galaxy. And you can see the time going along in days. And it got extremely bright. Unfortunately, we missed the very beginning, but we managed to catch it later on as it was fading. And we can see different observations, and the object faded in a way that was predicted for these tidal disruption events when the massive black hole swallows a star. And what was amazing about this particular one was that when we measured its mass, we found out that its mass lies right in this intermediate mass domain. So I said we found one intermediate mass black hole back in 2008, and now in 2018 we found another one. Another one we found in 2016. I didn't show this first because it's less convincing when you see the X-ray data. It doesn't look very exciting, but it's just here. You can see the tiny little galaxy, and the X-ray source became extremely bright. And again, we found out that this was also an intermediate mass black hole that was hidden in the center of this galaxy.
Natalie,
Yes.
I think there is another question. I'm not sure it's still up to date, but let's see. What did we see in the famous photo of the black hole if we're not able to see black holes?
What we see here is the matter that's spinning around the black hole. That's what we usually see in this X-ray images. If you're talking about what we're seeing in the Event Horizon Telescope, so this was an image that was published 3 years ago now, I think, that was made from radio observations. Now, this combined many, many radio observatories all across one whole hemisphere of the Earth. And there what we're seeing is a shadow of the black hole on the bright matter that's around the black hole. And that was in a different galaxy, a galaxy fairly close, but still pretty far away. So that was just the shadow that was cast across the bright light.
Thank you.
No problem. So, oops, sorry. So yeah, this is a very strange tidal disruption event, this massive black hole swallowing a star, because we saw it got very, very bright, and then it stayed bright. If you remember the other ones, the light seemed to drop off in the X-rays, but this one stays bright for a very long time. In fact, it stays above that Eddington limit that we were talking about for more than 10 years. So we've now got evidence that the Eddington limit can be broken. It can be broken by hundreds of times, and it can also be broken for a very long time. So there are many, many astrophysicists today that are working very actively trying to understand what the physics is behind these very strange sources that can go way beyond the Eddington limit, way beyond what we believe that they could be in brightness. So just to talk very briefly about the gravitational wave events. Gravitational waves are fantastic. It's unbelievable that we can now detect them. I'm still amazed. But there's been some extremely exciting results that come from gravitational waves. This is not a gravitational wave talk. I've been talking about what we can do with X-rays, and I shall come on to that in a few seconds. So just to remind ourselves about these gravitational waves, we've got two masses, either two neutron stars, two black holes, or maybe a neutron star and a black hole that are spinning around each other, like the Earth and the Moon, for instance. And so we see these ripples in space-time. So this is just an artist's view of what you would see if you could see these gravitational waves. But what we need is some very specialized detectors. So the first two gravitational wave detectors to come online were the LIGO detectors, and you can see these detectors, well, at least part of them. These are in the United States. So there's Livingston detector, which is in Louisiana, and Hanford, which is in Washington, in the state of Washington. And you can see this area where we detect the gravitational waves, thanks to the magnification that we see along these two long arms. So you see these two long arms here. These are what we call an interferometer, but it's not important. So these two detectors started to work. We have other detectors that have started to work since then. One called Virgo, which is near Pisa in Italy. And there's a new Japanese detector that's come online just in 2020, which is called Kagra. And with those, we've been detecting many, many, many of these gravitational wave events. So this is a very complicated plot. I'm just going to go through it very quickly so that you can understand what you're seeing. What you can see on the left-hand side, these numbers, 1, 2, 5, 10, 20, 40, are masses. The masses of the objects that we've been detected by LIGO, Virgo, and the other gravitational wave detectors. Every time you see something like this, there's two objects and they become one. This is a gravitational wave event. These are the black holes, the ones colored in blue, and the ones that are neutron stars are colored down here in orange. You can see them here. These are the neutron stars that have been detected before we had the gravitational wave detectors. They're not mergers, they're just simple neutron stars on their own. And these are the masses that we knew for the neutron stars. And the masses we knew for the black holes are these purple dots that you can see. And not one of them goes above 20 solar masses. So if I'd have given this talk maybe 10 years ago, I'd have probably told you that black hole masses couldn't be greater than about 20 solar masses, which is what had been predicted. And that's what we were seeing observationally. And LIGO, Virgo, and the other gravitational wave detectors have now been detecting many of them, and you will see they're much more massive. Now, why they should be detecting such massive black holes is not clear. And also, how the black holes get to be so massive. This is also something we're still trying to work on. But what I want to talk about are these objects down here. So there was these two neutron stars that merged through one of these gravitational wave events and made a huge explosion that was detected by 200 different observatories, including the X-ray observatories that I showed you. Now, we know there were two neutron stars, and we know the masses very precisely, and we know the mass of the object that was created, but it's just in this difficult zone where we don't know, is this still a neutron star, or is it a black hole? I said to you, black holes have got masses of between about 3 and 100 solar masses, but is it really 3? Is it maybe 2.5, or is it maybe 4? It's not clear. And what's the maximum mass of a neutron star? Well, we thought it was maybe around 2, but it could perhaps be as much as 3. So this object here that's been created, we don't know what it is. Our gravitational waves cannot tell us the answer, but X-ray observations can tell us the answer. And we're actively observing these created objects here with all of our X-ray observatories, trying to understand what it is. So I'm hopefully be able to tell you in a year or 2 years' time whether or not we've actually created a neutron star or maybe we've created a black hole. But yeah, this is work to come. So let me just give you a quick summary of the things I've been talking about before I share with you a way that you can actually get involved in this kind of research. So I think I've shown you that energetic and extreme objects are most easily detected in X-rays. You saw that in this beautiful E-Rosetta image. Many of the objects that we've detected are new kinds of objects, or very weird that we don't understand. The ultraluminous X-ray sources have now shown that they can host neutron stars, and maybe all of them even host a neutron star. We don't know yet. I've also shown you that super Eddington accretion is actually possible, but we have no idea how that can happen. We have many different theories, but we don't know. I also showed you that intermediate mass black holes exist, and we're now beginning to find a whole population which will help us understand how these supermassive black holes can come into existence. The compact objects that have undergone mergers that have been detected by the gravitational wave observatories have revealed really massive black holes, more massive than we expected. And we still don't know what the result of these neutron star mergers are. And hopefully, as I say, I'll be able to tell you the answer in a year or 2. And we have many other objects that have not been able to be identified yet. And probably there's other things still to be discovered. So how can you get involved? Well, recently we've produced this this platform that you can go to. The web address you can find, it's here. I'll put it on the next slide as well, and I can put it in the chat after we've finished. There's plenty of information on this website, tells you about the project. It gives you a tutorial, and you can find out how to try and identify these sources. Then it will take you through a way to practice identifying sources. And once you get a good rate of learning to identify the different kind of X-ray objects that we've seen with the XMM Newton telescope, it will allow you to start to classify new sources that have never been studied before. So if you are confident in English, you can go to this website in English. There's also a French version, or for any of you that speak either Spanish or Greek, there's now the Spanish and the Greek version online since yesterday, and we'll probably be adding some different languages. What do? And it shows you and takes you all the way through to try and understand what different objects there are. And you'll be able to find new supermassive black holes in the centers of galaxies, new stars, new X-ray binaries, and maybe some of these tidal disruption events or ultraluminous X-ray sources. And these are the kind of things that you'll be able to look at. So I'd like to thank you for listening to the talk. And I hope that we'll be able to see you on this platform, Claxon, sometime in the future. And again, there is the web address if you want to go along there and see if you can create yourself a login and get started and finding some new and weird objects in the universe. Thanks.
Thank you, Nathalie. There is a question in the chat. What bodies that never interact have approximately the same mass?
What bodies that never interact have the same mass? Is that the question?
Tristan, do you want to add anything? I'm just reading, so Tristan? I don't know, is Tristan still here? Maybe not. Well, I can send you the question in the chat. See if it's clearer. Tristan Lafortune, no. Okay. His microphone is broken, so I'll send you the question in the chat, Nathalie, and you'll see if it's clearer. I can't copy and paste, actually. So again, the question is, why bodies that never interact have approximately the same mass?
All bodies actually interact, and there's always going to be gravitational interaction between the bodies in the same way as I interact with the Earth, and that's why I'm stuck to the Earth and I don't float off into space. So all bodies will interact. So yeah, they could have any mass. I mean, whether it's a small mass like myself and compared to the Earth, or two masses that are very similar mass. I'll let you ask the next question.
I don't see any other question in the chat, but there might be other questions. Do you have other questions?
Is it possible to speak?
Yeah, sure.
Right. So it's a bit long to write it down on the chat. As I quickly understood it, is the Eddington limit concerns the spinning so in some way causes the mass to create its own ejection. Is it something like that? So if something is too massive, the centrifuge, I don't know how to say it in English, centrifuge force causes it to explode. But so that's how I understood it. But how does it apply to a black hole, as the matter is attracted by the hole? So I don't quite understand.
Absolutely. Yeah, centrifugal force. Absolutely. It's actually not the centrifugal force that is acting here. It's a strange thing to try and understand because we don't observe it on Earth. We don't ever observe the light pressure causing any kind of force causing the light from the sun doesn't cause you to be moved along or pushed away or something like that. But that's what happens in these objects that are accreting a huge amount of matter. So as the matter falls inwards, then we see a lot of light coming from the disk, and it's actually this light that's pushing the matter back outwards. So it's not the centrifugal force, it's the light of the matter that's in the disk that's spinning around the black hole. And this is why it works for a black hole, because you still have the matter that's spinning around the black hole. The matter's falling on very quickly, so the disk is very bright, pushes back the matter and stops any more matter falling onto the black hole. Does that answer the question?
Yes, just one question. So when a black hole is created, its size is actually set. It cannot grow any larger than that because it pushes matter, right? Or does it absorb the matter that is around it?
It's a good question. Very good. Right. So yes, the black hole will get larger and larger with time if there's matter around for it to absorb. So if you had a black hole right at the beginning of the universe, for instance, had lots and lots of matter around it, the matter could fall onto the black hole and it would get bigger and bigger. But because of this Eddington limit, it shouldn't be able to go above the Eddington limit. Whether it does or not, that's something we need to find out. Now we know that it is possible to go past the Eddington limit. And so if it can't go above the Eddington limit, it can only accrete matter. It can only have so much matter that can fall onto it with time. And that's why it could never get to these huge, big masses that we see if the black hole only started at, say, 10 times the mass of our sun. Is that clearer?
Yes, thank you.
I have a question. You said that nothing goes faster than light, but the space-time in which light propagates, it propagates in the form of waves at what speed?
Well, yeah, the maximum speed is the speed of light, so 3 times 10 to the 8 meters per second. The gravitational waves, whether exactly at the speed of light or slightly less, probably at the speed of light from what we've seen, but it might have a slightly smaller velocity. We don't know yet, but probably.
Can we measure the speed of waves, of these waves?
So what we do is with these gravitational wave events is that we wait to see the light that comes towards us from the electromagnetic emission, so either the optical or the X-ray or something else, and then see if it arrives exactly the same time as the gravitational waves. The thing is, we don't know if the gravitational waves are emitted before the light, and that's where the error comes in, that we can't tell exactly. But so we can't measure exactly the speed of the waves, but we can measure it with respect to the light.
Okay, thank you.
Are there other questions? So I just sent again the file. So of course I can find your names via Zoom, but it saves me a lot of time if you complete the file. I'll compare the 2 files, but honestly it's very long for 200 people. So please add your name, your major, and so on. I think there are new questions. Philippe Guillemont said that everything ends into a black hole. Do you think that's true?
I doubt it. As I said, a black hole is not just this huge big hoover that sucks up everything. You have to be pretty close to the black hole for it to start sucking up the material. So no, I doubt that everything will just fall into a black hole at the end. It's unlikely. But I mean, we don't know what's going to happen to the universe. At the moment, it's in expansion. So the universe is getting bigger, and it's in fact accelerating the size of the universe. But maybe at some point it will slow down and then maybe start to fall back again. It's called the Big Crunch. It's a theory. But we don't know what will happen if that happens. And we won't be able to be there for it either. It'll be in a very long time if it does happen.
Thank you. Well, I don't see any other question coming up.
Can I ask you a question?
Yes, sure.
Okay. I think that some physicians say that there are no black holes. What you can say about this?
Absolutely. There's people that doubt them. I agree. We know that there are regions in space that are very, very small and extremely massive. There are theories as to what this could be, which is why we'd like to measure exactly the radius of these objects precisely to be able to validate the theory of it being a black hole or being something else. I think the circumstantial evidence today points towards a black hole. The electromagnetic emission that we receive thanks to the light around the accretion disk, in the accretion disk around the black hole points towards that. But the gravitational waves we detect would only have that form if they were coming from either black holes or neutron stars. And you can distinguish very, very easily between a gravitational wave coming from a neutron star and a black hole. So it seems, especially since we've detected gravitational waves, it'd be very difficult to understand the majority of these objects if they were not black holes. But yeah, maybe there is also some strange object out there that we have not been able to identify.
Then we cannot confirm that there are black holes.
I think we can definitely confirm there are black holes, but maybe some of the objects that are possibly black holes are other objects too. But I would say today that yes, there are definitely black holes, but maybe some objects that we see as black holes could be other objects as well.
Okay, thanks.
So Jeanne asked a question in the chat. Could a black hole disappear?
So this was in the news recently that a black hole had disappeared, but the black hole doesn't actually disappear. It's just that the light around the black hole has been extinguished, and that will happen because there's no more matter to fall onto the black hole. So it happens with our tidal disruption events, these massive black holes that swallow stars, because at some point it swallowed the whole star and there's no more matter to swallow. It could also happen around smaller mass black holes as well. So yeah, the black hole will not disappear. There's also this idea you can have Hawking radiation. So you can actually lose matter from a black hole, but it's extremely slow. And it would only happen if you had a very, very, very small black hole that maybe was formed at the beginning of the universe. And that could have perhaps evaporated in the time. But otherwise, a black hole like the ones I've been talking about that weigh 300, 100, 1 billion times the mass of our sun, no way could it have evaporated in the time of the universe.
Does a black hole, can a black hole come near our solar system?
It's a good question. So there's been also some things in the news recently as well about a black hole that's not so far away from our solar system. It's still far enough away that it wouldn't cause any trouble if there really is a black hole in that area. Like I said to you, even if our sun became a black hole, it wouldn't suddenly suck us into it. The only thing that would happen is it would become very, very cold on Earth because there would be no more sun that's shining, which is a shame. So yes, I guess a black hole probably possibly could come towards our solar system. It's not going to happen anytime soon. And yeah, it would have to get pretty close for it to cause you a problem.
There are many questions. So the first one is, how is it possible, what is around the black hole if it's not matter? Because apparently you said, I forgot, but that there is no matter to absorb.
Right, yeah, so a lot of the universe is a vacuum. So there's not necessarily matter around. So you might have matter around a black hole because when the black hole was formed, there's stuff that's left over from the star that exploded, for instance. You can have matter around because, yeah, they say it swallows a star, or if it's eating a star that's close by. But yeah, if the black hole is nowhere near any of that kind of matter, it's a vacuum, so there's nothing there. So yeah, I guess that answers the question.
Is there a new life in the black hole or a second world?
So we can't actually see inside the event horizon. So it's as close as we can see. Only once the matter is dropped into the black hole, there's no more light that's being radiated. We can't see anything inside. The forces inside the black hole is gigantic. You can't even begin to imagine it. If you were to fall yourself into a black hole, the difference in the force between where your feet are and your head is so strong that you'd actually be spaghettified. So you'd become a long, thin piece of you instead of just being a human. So you're going to have to undergo all of those forces as you fall into the black hole. So it's very difficult to imagine that anything could actually live in there. Because, yeah, most of the forces would just rip apart anything that came towards it. As you see, the black hole already rips apart the star as it comes towards it. It's not when it falls into it, it's before that it falls into the black hole. So, yeah, I find it difficult to imagine anything living inside a black hole. But I'm not going to say never.
What is the maximum speed ever recorded for an object around a black hole?
Yeah, so the light is obviously going at the speed of light. It's the maximum speed that you can go to. Sometimes we see what we call superluminous light that seems to go above the speed of light, but it's only because of relativistic effects, and because the light's coming towards us, we see this relativistic effects. So it seems to go above the speed of light, but it doesn't. There's nothing that goes above the speed of light.
Do we find geons, if you know what that is, predicted by relativity theory? GEONS.
GEONS.
Tristan
Sorry,
L. I'm not sure what the last word is. I send the word in the chat, but obviously I have no idea what geons are.
Sorry, no, nor do I. I've looked in the chat, but yeah, I'm sorry. I can't answer that question. I'm sorry.
Thibault asked, would a black hole come to us, or are we going to a black hole? Which of us is moving towards the other?
So, yeah. In the same way as I said earlier, the reason why you don't float off into space and you stay on the Earth's surface is because the Earth attracts you, but you also attract the Earth towards you. Okay, so this is just simple gravity. So yeah, the black hole will be coming towards you, but you'd also be going towards the black hole. If you're talking about these massive black holes, then obviously you'll be traveling towards the black hole faster than the black hole is traveling towards you.
Can we one day measure the Hawking emission to detect a new black hole?
That's a good question. Not with any of the instruments that we have today. either that would have to be very, very close. But we don't know any black holes that are that close. So yes, with a very sensitive instrument and a black hole that was fairly close by, but not with any of those that exist today. So no, not today, we can't, but maybe in the future.
Oh, I've got another excellent question. If someone jumped into a black hole, assuming that he didn't die, would he see the future of the universe due to time dilation?
No, he wouldn't see the future of the universe, I'm afraid. So yeah, it's not a good idea to throw yourself into a black hole just to try and see the future.
Okay, does a black hole break the second law of thermodynamics, since matter can disappear, I guess, in a black hole?
Right, no, it doesn't. And so, which is where some of this idea for the Hawking radiation comes from. So no, it doesn't. But it's complicated and it's not something I'm going to go into here, I think.
Is it possible to make a black hole?
So is it possible to make a black hole? Is that the question?
Yeah.
Right, yes. Yes, so when the Large Hadron Collider was switched on, they thought that the Large Hadron Collider might make some mini black holes. So the Large Hadron Collider is an accelerator which is below Switzerland and France. The idea of the Large Hadron Collider is to accelerate particles to almost the speed of light and smack them together so that they create subatomic particles. So we can try and see particles that we've never detected before. So maybe some very, very, very small black holes could have been created in the LHC. None have been detected to date, but they'd be so small that they would never accrete any matter, so they'd never get any more massive. They would be so small that the next particle of matter that was close by would be so far away that it would never fall into that black hole. So even if they created it, it would never get any more massive.
Are there results from the Russian X-ray space telescope SPECT-RG or the Chinese X-ray space telescopes?
Right, yeah, so SPECT-RG is the telescope that has got eROSITA on it. So I showed you the results from the X-ray observatory eROSITA. So SPECT-RG has also got a Russian detector on there. It's much harder X-rays. So far, none of that data has been published, so we don't have any information from the harder X-ray observatory that's on SPECT-RG. I'm sure it will come out at some point. I think they've been focusing a lot on what's been done with eROSITA. There's been some fantastic results come from eROSITA. It's discovered some very weird and strange objects that we didn't expect to exist. Many, many more objects that we were hoping to find as well. And I guess the data will come. The first major X-ray observatory that's going to be launched by the Chinese is the SWAM Observatory. This is a French-Chinese collaboration, and this will be launched. Now it's been slightly delayed. It'll be launched in just over a year's time, so there's no data that's come from that yet. But that's mostly expecting to detect gamma ray bursts, gravitational wave events, and probably things like these tidal disruption events that I discussed.
Why is it interesting to study black holes, even if we will probably never be able to exploit them?
There's many reasons to study black holes. So a black hole has got a very high gravitational field, a very large gravitational field. It's very, very strong. And it's the best area we can study general relativity. So you might think that there's no reason to study general relativity. General relativity is the best description of gravity that we have today. The previous best description was one by Isaac Newton. And we thought for 300 years that Isaac Newton's description of gravity was perfect. Every now and again, we found some kind of little problem with Isaac Newton's gravity. And that's how general relativity was born, is because we realized there was some additions to be made to Isaac Newton's gravity. It's possible that there's still additions to be made to general relativity. Maybe Einstein's not got the whole thing. Maybe there are some minor corrections to be made. It might not seem important in everyday life, but if we didn't have general relativity, your GPS wouldn't work, for instance. We wouldn't be able to deal with the satellites in space. We need that extra correction to Isaac Newton's law of gravity to be able to do such fine apparatuses to use. So we study the general relativity around the black holes to try and see if there are any extra additions to be made that we might need for future, I don't know, technological advances that we might make. So that's one good reason to study black holes. That's if you want to have some kind of use that's going to be useful to everybody. It's fascinating as well. I think that people want to know what's out there. That's why you have explorers. That's why people went to America, to India, and wherever else to try and find out what else was out there. And in a way, that's kind of what we do in astronomy.
Arthur would like to ask a question. Of course, you can ask your questions yourselves. You don't need me. So I'm only reading the questions in the chat, but you can do it yourself. Arthur, what is your question?
Thank you. So I will ask you, what would be your vision, your prediction about the study of astrophysics or black hole study? What would be the next step or the next discovery about the study of black holes or the universe in your vision?
It's a really good question, and I'm not sure I could give you any interesting answer, to be honest. We've been so overwhelmed with new information in these last years. So, and it wasn't until 2008, for instance, that we realized that there were already some intermediate mass black holes. So that already was something we were like, oh, okay, so there are intermediate mass black holes, even though they've been predicted. That was one thing. The fact that we can create black holes of the masses that we've been seeing with the gravitational wave detectors is another thing that's really blown our minds. As I said, we thought that the stellar mass black holes could only go up to 20 solar masses. And then we said, oh, no, they can go up to 80 solar masses. But at 80, it's like really impossible to make something bigger than 80. And then we detected several now. There were at least 2 that fall into that mass range with the gravitational wave detectors. And now people are saying, oh, no, okay, so we need to refine the theory now. And people are coming up with theories how you can create a black hole of 85 or 90 solar masses directly from a star where it was not thought to be possible. And I don't know, I would suggest that it's the gravitational wave detectors that are going to carry on pushing the limits of our knowledge in the near future, and that because that's what's been going on the last 5 years. And I think we're probably going to discover many new things through these gravitational wave observatories, but I couldn't tell you what. They've taken us by surprise. Another thing that the gravitational wave detectors have discovered is, I mean, if you read any paper on gravitational waves that was published before 2015, they all say, yeah, it's going to detect loads and loads of neutron stars merging and hardly any black holes merging. And why? We've discovered nearly only black hole mergers and hardly any neutron star mergers. Why are we not seeing black hole neutron star mergers as well, for instance? I mean, I guess these kind of areas are going to have to be investigated and try and understand. So I guess it's going to come from the gravitational wave detectors, but what it is, who knows? It's just been a really fascinating few years.
Thank you.
I have a question. It's about how does it work for a black hole to not implode in himself, because when it's about a star, the electromagnetic interaction between everything goes in the other way of the gravitation of the star. But how it works for a black hole, I don't know if it was clear.
Yeah, it's a good question. So you're talking about on the inside of the black hole. Is that right?
Yeah.
Right. So there are many, many different theories about how it works on the inside of a black hole. As I say, it's very difficult to test any of those theories because we can only see up into a certain radius around the black hole, this event horizon. They're all quite diverse. I can't sort of give you a global view because many of the different views of the inside of a black hole are actually quite different. I think the short story is we really don't know what goes on inside the black hole. There's a lot of work that's going into that in theory. It's possible that you would just have this like infinitely dense point-like thing right in the very center of your black hole. It might actually be much larger for some reason, that there is some kind of force that be able to balance the different particles that within the black hole. It really is not clear at all. So I'm afraid I don't have a good answer for you.
I think there are many more questions. What was the last one? Well, I think I already asked this one, that one as well. What is the link between a wormhole and a black hole?
So yeah, wormhole has been predicted to exist. That the idea being that it could pass from one region of space from the black hole to another region in space. It's a mathematical model that's not been demonstrated. It's unlikely that it could exist in reality. You have to realize that there are a lot of different mathematical models. I mean, there are different mathematical models for a black hole, for instance, but in reality, in astrophysics, there's only two kinds of black hole that really could exist. So the idea is that you could have, mathematically speaking, a black hole that's got a charge, like an electron or a proton, so it could either be positive or negative. But in reality, there's going to be particles in space that, if it was a negatively charged black hole, for instance, those particles would be attracted directly to your black hole, and therefore you would not have a charged black hole. So mathematically you could describe that, but it's just not going to exist. And I think that's probably the case with the wormhole. That's my thought on the matter. Maybe someone else would say something else.
Do you have time for a few more questions? I think they are very inspired tonight.
Yeah, a bit of time.
All right. How did you react when you saw the first picture of a black hole?
Right, so we've not actually seen a real picture of a black hole. We've seen the shadow of the black hole with the event horizon. It's good. Actually, what I showed you with the X-rays is actually we see the light that comes from even closer to the black hole than what we see with the shadow with the event horizon. So yeah, it's exciting. I'm actually probably more excited by gravitational waves, I'm afraid. Sorry.
Could we live near a black hole?
How near would near be? No. We need the light from a star to live. We need the energy that comes from somewhere. A black hole doesn't radiate. The matter around it does radiate. But the nature of the energy that's coming from the matter radiating around a black hole would not be healthy. It would be like having an X-ray all the time, and you know you're not allowed to have too many X-rays every day or every year. So yeah, you wouldn't want to live near to a black hole if it was accreting matter. If there was one that was not so far away and there was also a star, then yeah, you could probably live fairly near, but not too close.
Is time a kind of matter?
No. Time is not a kind of matter. Energy is a type of matter, but not time. Time is one of the dimensions of space. So time you could think of as a length, but not a mass.
We often said that all information about matter that fall into a black hole are lost. So what type of information could we recover from Hawking radiations?
Right, so with a Hawking radiation, you can have a particle that will split into a particle and an antiparticle. So antimatter, something was expected to exist everywhere in the universe. It was thought that it could perhaps exist right at the beginning of the universe in equal proportions to the amount of matter. But that's not what we see today. We see a really asymmetric universe where the majority is matter, and that's what you're made up of. And then there's antimatter. You wouldn't want to meet your antimatter self, because then you would annihilate and you would not exist anymore. So a particle can actually spontaneously disintegrate into its matter and antimatter self. And if that was to happen directly at the event horizon, one of those particles could like come out and one would drop in. Okay, so that's how we'd have your Hawking radiation. I don't think you'd be able to get any coherent information from that. So I'm not sure you would be able to derive much information. At the moment, we still can't detect that radiation. So I guess the question's not really been posed.
Okay, a lot of thank yous. Could matter or light escape from a black hole?
Yeah, I guess I probably just answered that question. Yeah, the Hawking radiation, thanks to this spontaneous disintegration of a particle into its particle and its antiparticle.
Where could we find some documentation to learn more about what we talked today?
So I definitely go onto the Claxon website. Even if you don't want to try and identify X-ray sources, there's a lot of resources on the Claxon website. You can send me an email. I can provide you with my email address, and I can point you towards some more documentation as well. I'll put my email address into the chat. There's a lot of information out there. Yeah, I could point you to a few different sites that might be interesting to read.
What is your opinion on the white holes?
I'll just put my email address into the chat. I don't actually have an opinion on a white hole, I'm afraid. Sorry, no, I can't answer that question for you.
Would you say that antimatter is in reality matter that goes in the opposite direction of time?
No, not at all. Antimatter is matter in the same way as any other matter you see. It's been predicted you could have antimatter stars, for instance. We see antimatter in the central regions of our galaxy. We don't know quite what's producing it. It might be produced from the X-ray binaries I talked about. It might be produced around the supermassive black hole at the center of our galaxy. But antimatter, yeah, it's not necessarily going a different way. You can imagine it going in a different way because I talked about that particle coming up and matter and antimatter, but yeah, they don't necessarily go in two different directions. But especially if they do, otherwise they're going to annihilate and you're going to get an explosion.
Excuse me, can I do another question if you have time? I would like to ask you, what do you think about the movie Interstellar and the physics, the science around the black hole mystery, etc.?
I've not actually seen the film. I'm really sorry. I do know that the actual images in Interstellar are accurate. So when you see the black hole, you see the accretion disk that I was talking about. You see the matter that's spinning around the accretion disk. But because of the effects of general relativity, you actually can see the back side of the disk at any time, because you saw the mass of the black hole deforms space-time. And so actually the light that's coming from the back actually goes around this curved space-time where the matter was. And so you see the back of the disk, and that's why it looks like it's coming up at the back. And these images were produced by people who work on black holes and actually do proper modeling of black holes. So I can tell you that the images are good in Interstellar, but I've never seen the film. I'm sorry, I should see it at some point.
Okay, I knew it because it was Astrophysics to Kip Thorne, I think, that wrote the equation for the black hole.
Absolutely.
Image.
Yeah. And he also, the guy that was involved in doing that, also was the person that got the Nobel Prize for the gravitational wave detection. So it's the only person to have got an Oscar or a Nobel Prize or something like that. So.
Okay. Thank you.
Yeah. Some of our students have to do a presentation this week on this movie, so they will probably have some answers. I think I probably missed a lot of questions. There is another one here. So if the big crush is false at the end, I'm not sure what it means. We will have a black hole, and after that they can disappear with their emissions to leave the universe with nothing. I don't know if it makes sense.
Yeah, it makes sense. So yeah, this was this idea that I said that at the moment the universe is expanding and it's accelerating in expansion, and maybe sometime it will like slow down, and then the whole universe might start to collapse on itself. But we don't know what's going to form at the end. It's in the same way as we don't know what there was before the Big Bang that created the universe. It couldn't have been a black hole, otherwise you wouldn't have got all the matter exploding out of it. So there's no reason necessarily to imagine that it will become a black hole at the end. But yeah, we don't know. I think that's probably the easiest answer, I'm afraid. It's probably not what you wanted to hear, but we don't know.
I think that was the last question, unless I missed one. So I also read a lot of thank yous. So thank you, Nathalie. And I think there are a few links that might be interesting for everyone that Space Kiwi just sent. So the talk will be available on their YouTube channel. And you've got their website as well, if you want to know more. There might be one last question.
I see one. Could Superman escape from a black hole? No, he couldn't. Sorry. No, thank you for inviting me.
Thank you. Have a good evening.
Yep, thank you. Have a good evening as well. Bye.
Bye-bye.
Thanks.
Thank you. Bye.